this is A8. This is our last topic that will be on the next quiz. So A5, which was the factoring, cancel, square roots, complex fractions, algebra assignment. A6 which was check both sides of the limits. A7, which was super high level, but in the end, if you can do one of those two things, you're in good shape. And now finally, A8. We're really just going to put a lot of things together in this one that we've already kind of been talking about. So we'll kind of look at that. We've said that limits have equal infinity in the past, and what we're going to develop in this section is still answering limits like that, but doing that without looking at the graph. So we're going to have a function like this in the end, and we're going to be asking you really one of two things. We're going to ask you for a limit as x goes to something, and that limit is going to be either plus or minus infinity, and that's where you've got to figure something out, right? Because you have to decide whether you're putting plus infinity or negative infinity. And then remember those limits being infinity always mean you have an asymptote. So we may ask you that question as well. It really ends up being the same question in the end. You're doing the same math in both of them, but then you've got to identify those limits. Well, which limits actually give me infinity? And it's all stuff that should pretty much make sense as we go through it. So here we go. We have a function. It's two polynomials over two polynomials, or two quadratics even. X squared plus x minus 6, x squared minus 3x plus 2. Both of those can be factored. So let's get that done. Neither one of them are super hard. And we should end up with a factor in common, numerator and denominator. So x squared plus x minus 6. What two numbers am I going to use when I factor that? Plus 3 minus 2, right? Is that what I heard? One of those is going to repeat in the bottom. X squared minus 3x plus 2. Yep, minus 2 minus 1. X minus 1, x minus 2. Order doesn't matter. I set it up so the x minus 2s were at least on top of each other. Why would I factor something like that? Because I can't do any cancellations unless I'm pure multiplication. I'll still keep seeing it. I know I will, but I have pure multiplication. A thing times a thing. Any of those things can be crossed out if you find a copy of them in pure multiplication in the denominator. Okay. I'm not working in a limit here, so I'm not going to show any cancellations. Right. Letter A. What is the domain of f? Let's start there. So really when you're working with a rational function, which is these guys' names, identifying the domain is really just saying which numbers don't work. So what numbers am I not allowed to plug into f of x? That's it? You were still looking. That's why I was not responding. Negative 3 is actually okay, though, because I'd get 0 times a non-zero, which would give me 0. And my denominators would both be non-zero. So 3 is actually, it's a number negative 3 is an important number for this, but it's actually in the domain. 1 and 2 are our numbers because they make the denominator 0. So when the question is what's in the domain, we've got to look only to the denominator. Now, in a minute down at the bottom, we are going to incorporate negative 3 in our work, so it is a number we have to find. But all of the numbers except for 1 and 2 are in our domain. So we are going to go ahead and just write that out as negative infinity all the way up to 1, together with 1 to 2, together with 2 to infinity. And we've been doing domains like that since Algebra 2, right? Okay. All right, I'm going to pop that graph in Desmos. So we're just going to make a sketch of it. We got, it doesn't matter whether I do the factored version or the unfactored version. They are the same graph. X squared minus 3x plus 2. All righty. All right. We end up with a very common looking rational function graph, two kind of shapes that kind of mirror each other across a diagonal line. We have an asymptote. It looks like it's going to be at x equals 1. So one of those two numbers that you just gave me in the domain gives us an asymptote. but the other one doesn't. So sketch that loosely on your graph. We also have a horizontal, I think we have both as we have a horizontal asymptote of 1 and a vertical asymptote of 1. So you might want to kind of just sketch your graph so it looks like that. And I'll put those in while you guys are doing that. X equals 1. Y equals 1. Boom. Boop. And we'll make those dotted lines. Okay, there we go. So there's our graph. We're not worried about the horizontal asymptote today. That just kind of happened. That is for A10. But that vertical asymptote. There's something that Desmos isn't showing you guys because, man, we just said that you cannot include 2 in your you can't include 2 in your domain. And sure enough, if I take my cursor in Desmos and bring it up to 2, never easy to do, but there it is. No hands. You should also make your graph look like that so that at about 2.5, doesn't have to be perfect, at about 2.5, you've got a hole in your graph. All right, so I'll do that over here. Yeah. Boom. All right. Everybody good with that? Cool. All right. My poorly drawn, it's definitely harder to draw on on a screen like this than it is on a piece of paper, but there is my rough example. That's what the graph should look like. So which x values in the domain produced an asymptote and which did not? Which x value is not in the domain? Which of the numbers that we left out produced an asymptote? Obviously, hi. No, you're good. I do. Right there. There you go. You too. All right. So x equals 1 produced that vertical asymptote of x equals 1, but 2 didn't. And the reason why is, so 1 gave us a vertical asymptote. Two did not. The reason 2 did not, let's start there, is because if I calculated that limit as x goes to 2 of f of x, I'd be plugging into x plus 3 over x minus 1. So I'm looking at how little space I've left myself, but I do want to show us this. X plus 3, x minus 1. So what I have written there is the canceled version of f of x, right? And that gives us 5 over 1, which is where the hole is. So when these limits come out, a number versus does not exist, that's giving us information about what the graph looks like without graphing it. If you get a limit, you're not going to get an asymptote. If you get a limit that exists, I should say, you're not going to get an asymptote, you're going to get a hole. If you get a limit that is infinity or negative infinity, a limit that does not exist because of infinity, you're going to get an asymptote. But that should make sense because that's what that infinity means. Infinity means that I can get up as high as I want. I just need to get closer and closer to that number. Plug 1.01 into that function, it's going to give you a really high result. You want to go higher? 1.001. You want to get even higher? 1.0001. That's what that infinity means. So 1 gave us a vertical asymptote, and when it comes time to actually answering that question, not just for our sake, but as the answer to a problem, we always give a limit. And we're going to evaluate these down at the bottom too, because the limit as x goes to 1, your choice, plus or minus. I'm going to choose minus here. I'll go in from the left. And as I come in from the left, am I going to positive infinity or negative infinity? Negative infinity. So that's the main thing. Like that is the main thing we're learning in this A8 is now kind of just like formalizing what we've been doing. One of two things happens when you get a function like this and you take a limit. And it really depends in this function on which x value you go to. If you go to 2, everything cancels out and you get a number, that drops the hole in your function. If I ask you for the limit as x approaches 1, if I said 1 overall, you'd be saying does not exist because we don't have matching infinities. But 1 left gives you negative infinity and 1 right gives you positive infinity. And because of that, you know the graph has an asymptote. That's the main idea of today's lesson. All righty. So just to formalize that, we did say 1 left was negative infinity. We said 1 right, without saying it, was positive infinity. Overall, the limit as x goes to 1 does not exist. And the limit as x goes to 2 goes to 5. I kind of jumped the gun on that part in my explanation for B, but you get a limit, you get a hole. I mean, I shouldn't say a limit always gives you a hole. If I took the limit, it's got to be a limit at a discontinuity. If I took the limit at x goes to 4, whatever that value is also the value of the function. It's not a hole. So we definitely need to be looking at discontinuities in order to be saying either of these two things. So if I know I have a discontinuity and I get infinity, I definitely have an asymptote. If I know I have a discontinuity, but I get a result, then that thing is a hole. Does that make sense? If I'm working somewhere where there isn't a discontinuity, doing the limit and doing the function are all the same thing. I'm just figuring out what the function value is. Oh, cool. All right. So it is going to be your job to take a look at a function like I have in the initial example and give me those infinities without looking at the graph. And the way we do that is we make a sign chart for our function. And I'm going to show you how to do that. So when you make a sign chart, you've got to do a couple things. You're going to draw a number line. You're going to label it with what you're making a sign chart for. We're making a sign chart for f of x. And then we need to find all the zeros of the numerator and all of the zeros of the denominator. So we're going to put lines. This is a number line in the end. We've got to find the zeros of the numerator and the zeros of the denominator. And that's where that -3 comes in from that we talked about before. -3 is a number that we need, and so are 2, and so is 1. Now, normally I wouldn't write this part out, but I want you guys to have this in your notes so that when you look back, and I'm also thinking about some of the work that I graded for BC and some of the mistakes that they were making, I want you to kind of see this. So we have 3 numbers that we have to put on our number line. Got to put them in order from least to greatest because it's a number line. So I'm just going to make 3 hash marks and label them -3, 1, and 2. They do not need to be evenly spaced. I mean, like, I made them evenly spaced, but I mean, they don't need to be like proportionately spaced. Like 1 and 2 are 1 apart, but they're 4 apart. Like, you don't have to show that. And now here's what you've got to do. You've got to take a look at the whole function, and each one of those numbers matches a factor. And for each factor, you've got to decide what this factor gives you based on where you are on the number line. So this factor is x plus 3. If I plug a number smaller than -3 into x plus 3, will that result be positive or negative? Negative, right? So -4 plus 3, I haven't added enough to get me back into the positives, so I'm going to put a negative sign there for the x minus 3. Now, I'm going to give a shortcut to this, but what I have to then do is look at all the other intervals. What if I put a number between -3 and 1? So something that's bigger than -3 into this, that's going to give me positive or negative? Positive, right? Because now if it's bigger than -3 and then I add 3 to it, that's going to get me over the 0. So I will actually be positive. But it does turn out that, you know, once I'm past that -3, if I then ask that same question about a number between 1 and 2, well, Well, yeah, a number between 1 and 2 plus 3 is going to be positive. Once you make the change, as long as it's all just these nice x pluses and minuses, it's just going to be the same after that number. So you really only have to look at the number itself. X plus 3 is negative before negative 3 and positive after it. I'm going to do x minus 1 next. What I generally do is I put the signs where they are in the fraction. So those were above the number line. I'm going to put these ones below the number line. It just helps me organize my work, especially when I'm writing in not colors. So now I've got x minus 1. The number I'm concerned with here is positive 1. And just like the last time we asked these questions, if you're smaller than 1 and you subtract 1 from it, that's going to make you negative. So you're negative before the 1 and positive after. And we'll finish off with our x minus 2. There are 2 x minus 2s there. Without taking any shortcuts, if you want to show everything, I'll talk about the shortcut in a minute. Got to kind of talk about both. You need a sign for each of those x minus 2s. X minus 2 goes with 2 in our sign chart, and plugging numbers smaller than 2 makes you negative. So I will be negative in the first 3 sections. And then positive when you plug a number bigger than 2 in it. All right, I think I can finally... Does that make sense how I did that? What you're really doing there is you're saying to yourself, like this sign chart is telling you that if you pick any number between negative 3 and 1, and you plug that in, this is going to give you a positive number. These 3 are going to give you negative numbers, which means that the result is going to be positive times negative on the numerator, and then negative times negative in the denominator. So overall, you'll have a negative times a positive. You know that any number plugged in between negative 3 and 1 will give you a negative result. So I usually do a overall somewhere. Sometimes you have less signs there. I'm just going off the chart for it here. And it's really just even odd, right? Do I have an even number of negatives or an odd number of negatives? So anytime I have an even number of negatives, they'll all cancel each other out. Anytime I have an odd number of negatives, they are going to, Anytime I have an odd number of negatives, I'm going to be, something feels off, right? I gotta double check this one. Anytime I have an odd number of negatives, I'm going to be negative. And anytime I have an even, it's going to be that. Yeah. I'm good. Yeah, I'm good. Sorry, I was thinking this dot was at 1 and I was confusing myself. This does match what we have. This does not match what we have. X is less than negative 3. Oh yeah, it does. Sure does. When x is less than negative 3, and man, boy, did I luck out and hit that one right on the head, our graph inches into the positive numbers. Yes? Oh yeah, something's off there, right? The green should match. Thank you. You are correct, because the green should match, right? Yeah, I just goofed up when I was doing it. These were on 2. Thank you, Will. Yep. Yes. So this is, yeah. Yep. Good catch. Yeah. I mean, that was the nice part about color coding it. I was able to easily see, goofed there. And this was a purple plus. Yeah. Yep. Which then makes this overall positive. Boom, boom, boom. All right, cool. And that's a 2. Got it. All righty. Yes. So now it really, it should match. Yeah. So up until negative 3, we were positive. We shot down into the negatives. But what that's telling us is if we have an asymptote at 1 and we're coming in from the left, we better be writing negative infinity, right? If we have an asymptote coming in to 1 on the right, those values have to be positive, which is how we get our positive infinity here. So these overall signs end up being, if you have an asymptote, what sign you're using on your infinity. So that's what we're doing in these problems. That's how we're going to be able to answer these without having this. Make a sign chart and then use the minuses and plus to decide whether you're going to use your minus infinities or positive infinities. It's on you to do this first. I'm not doing anything with the number 2 because 2 isn't an infinity, right? The limit as x approaches 2 is 5. So that we didn't need the sign chart for. We needed the sign chart for 1. Okay, so if you need a rule to show you how to do this, you need to use a rule is make sure you use every single factor as many times as it shows. If you have a factor that cancels, you can skip that on the sign chart. As long as you know what you're doing and you do it right. Those green pluses and minuses didn't do anything to the black overall signs because here I had a pair of negatives which canceled. Here I have a pair of negatives which canceled. Here, after we fixed it, I had a pair of negatives which canceled. And here I had a pair of positives. If I made these black marks just based on the pinks and blues, I'd get the same results. Okay, so a sign chart does not require the x minus 2s, but that's an extra thing for you to remember, like, oh, I can skip this part and I'm correct in doing that. Does that make sense? So it's up to you. Like, you decide, you do you. Like, are you good with that? Awesome. If you want to just be like, nope, I want to get it right all the time, stick with them. That really comes for any pairing up of factors, whether they cancel or not. If I had 2x minus 2s on the bottom, I could leave them out of the sign chart because they're going to do the same thing. And 2 minuses make a positive, 2 positives make a positive. They have no effect on it. Questions? All right, let's do one more example. All right. All right. We good. I really want to emphasize good notation in this. So we are now at the point where we've said it a million times, but we're kind of formalizing it. Some of these limits are not going to exist. Some of these limits are going to exist. If the first thing we need to do before we determine, normally this stuff isn't written down for us, determine what our limits are, is decide what form we're in. When I plug 1 into this, actually, let's factor it first because that makes life a little bit easier. I'll end up with x minus 3 over, no shock, x minus 3, x plus 1. Yeah. When I factor this, now that it's factored, this is easier to do. 1 is going to give me not 0 over 0, right? Because this guy's going to turn to 0 and the whole thing's going to multiply out to 0. So this is going to give me an asymptote. This is going to give me a does not exist. Because those are supposed to be x goes to negative 1s. That's why. Thank you. Probably, yep. Same issue when I did this in the other group. Good catch. Yeah, those are supposed to go to negative 1s. I have that factored right, correct? Yeah. The factoring's correct, yeah. No, but it's just a typo on that one. I fixed like 3 or 4 other typos in this one. I missed that one. Okay, good catch though. But yeah, so minus 1 is going to go to 0 there. On the other hand, 3 is going to give us a 0 over 0 situation. We can clearly see that those will cancel, so we're not surprised that when we get an actual value here. So with this notation, we're ready to just go at our problem. With this, I want good notation to show that I'm in a 1 over 0 or a non-0 over 0 situation. And the way we do that is we write the numerator limits and the denominator limits out separately. So we'll write the limit as x goes to negative 1, the limit as x goes to negative 1 of x minus 3 and x squared minus 2x minus 3. Negative 1 minus 3 is 4, negative 4. And the denominator is going to give us 0 because it has the x plus 1 in its factoring. You can skip that without doing negative 1 squared minus 2 times negative 1 minus 3. Once you see that, that now tells you the whole thing overall is going to be 0. Okay. So that's good notation. That's showing me non-zero over 0. That's why I'm going to be writing infinities. Next, we do a sign chart. We need two numbers in our sign chart. We need -1 and +3. We need a sign for each of the x minus 3's unless we're taking a shortcut. That's going to be negative before 3 and positive afterwards. And those signs have done nothing for us because in each case, they both make positive. But that's okay. If you want to get it right, I suggest doing it that way. Take your x plus 1. That's going to be negative before -1, and positive afterwards. Your overall signs are negative, positive, positive. We'll use those signs to put the signs in front of our infinities. -1 right is, to the right is positive, positive infinity. -1 left, to the left of -1, we have a big negative sign. That's negative infinity. If the infinities don't match, the overall limit does not exist. They all do not exist. But there's nothing better to put for x goes to 1. All right. So that is all the good notation if I gave you that problem. Like that's what you would want to write down if you were just given the problem that I put a star on. You would want to start at the top and work your way down. Yeah, I'm going to do that one next. Yep. X goes to 3 is a factor and cancel limit. So this is A5. I can just do this the way that I've been doing it. I just need to write out a new problem. I don't need to do any work up at the top. Limit as x goes to 3 of x minus 3 over x minus 3 times x plus 1 equals 1 over 3 plus 1 equals 1/4. So that's A5, right? A really simple A5. This limit equals this limit. I plugged in, that's a 3. It doesn't look like it, but that's a 3. I'll fix it. Gives us 1/4. And I know that I'm going to get something there because the 3's factor and cancel out. Because we know, looking at this, which ones are going to come out as infinities and which ones are going to come out as numbers. If it doesn't cancel like x plus 1, I've got to do all of this stuff because I know that limit doesn't exist. Even if I did cancel those x minus 3's, I'd have a 0 in my denominator and a non-zero in my numerator. That's why we did that this way. When I see this limit and I look at the factoring, I know my 3's will cancel, my x minus 3's will cancel. That's why I go this way. And that's the thing now where we're at. We've got to know which direction we're going in. Are we completely cancel or are we not completely cancel? Not completely cancel, completely cancel. I mean, in this case, it was not cancel at all. Whew. Yeah. Right. Yeah. Yep. Yeah. All right.